Hello there. Let's look at today reaction kinetics. So kinetics is fast, how fast something is happening. So think about a car. You drive a car 50 kilometers per hour, something like that, right? So this video we're going to talk about the rates, the PE diagrams, activation energy, and reaction order. So those are the things we will discuss today. So if you're not looking any of these items, look for the other videos. Okay. All right. So, um, so before we get into that one, something we want to understand the spontaneous and the non-spontaneous or spontaneity. That is nothing to do with the rates or how fast something is happening is not the spontaneous and non-spontaneous. That means whether something easily happening or not the speed. But if you look at this one, H2 and O2 will combine pretty fast to make water, right? So so that's a spontaneous reaction. So that means normally it's an exothermic, and that's the delta H minima, delta S max, and that's just the typical pattern. Versus we can think carbon plus, sorry, no, this is not a good way. So we want to go CO2 breakdown. Actually, that's a better way to do it, right? So that we need more energy to do it. So but this type of process, it's this way: CO2 breaking down to carbon plus oxygen is not an easy or not spontaneous. You can do it, but it takes a lot of energy. Otherwise we can put a catalyst, and at the end of your muffler in the car, and then we can perhaps get rid of all the CO2. That's not going to work, right? So that's something to do with the spontaneity. Let's not mix those two, okay? Now, so look at this reaction. So NO2 is gonna react with itself, and it's going to produce something. This reactant is going to fade away with every second because it's reacting and it's losing. The reactants are losing. So the molarity of this NO2 will be, every second will be lost like this. So it's a good way to look at it. So you can actually graph it this way, or you can table it first, 0.1, 0.01, 0.001, and so on, right? Or you can say 0.8, 0.6, 0.5, 0.3, and so on. It's depleting. That's what's happening. But as you deplete, you're going to make oxygen and 2NO in this case. Those are products. The green ones are products. Now what happens? Products with started from 0, and it's going to keep increasing slowly. The same thing, NO is making twice, so it's going to be even more than the oxygen, right? So these are the molarities we show. This is how you show it in a graph against time. So this understanding is important, right? So now we have the idea, like we said, losing reactants over time shows how fast the reaction is happening. So we can say minus delta NO2. Delta is a change. This triangle is Greek delta capital, so it means losing something. So if you lose twice NO2 over time, that 2 is the coefficient, and so it will be the rate. Now that will be equal to actually production of oxygen. So that's gaining of products plus P over T. You can say change of oxygen, positive, the gain, over delta T, right? Or you can simply say NO also, but NO you get twice, so you have to divide by 2. That's just the coefficient, right? Just know that way. And so for any reaction, you can write it that way and divide it by its coefficient. Now, if I if I tabulate the numbers of losing reactants, you can actually start with this table, or vice versa, right? Sometimes you're going to have to go from the table to the graph, right? So, but you understand how to do the graph. That's the first step, actually, understanding this kinetics. All right. Now, so let's look at bit more details here. Now, if I have this losing reactant, and if I draw a tangent, it's a tan theta or slope m. It's actually rise over run in this case, y-axis, change of the y-axis divided by change of the x-axis, right? and also it's the units are moles in the y-axis and seconds in the x-axis. That's why moles divided by second. That's the rate actually. So this initial one we called, actually it should be in initial rate. It's not instantaneous. So I'll change that. So and it's this tangent is losing and losing. It's getting lesser slope as you go down, right? And if you take a random place like something like that, that is actually the instantaneous rate. So that means we pick one point, so that's the instantaneous rate. And at the beginning what you have is called the initial rate, just the literal meaning, right? That's the fastest ever you're going to find in a reaction. So the initial is the start, that's the fastest. And then if you get the 2 points, that's actually the average rate. That means overall time or overall change of moles divided by the overall time. So that's the average rate. So there are 3 things you learned: average rate, initial rate, instantaneous rate, right? So all these 3 can be a good question for MCQs, right? Now let's see how fast a reaction can occur. What can you do to make it faster? Of course you can warm it, right? Look at this one. At 0 degrees some water versus 20 degrees water, they're kind of pretty dancing and moving fast, and the reactions are faster at 20 degrees compared to the 0. Now the other thing is concentration. So that means how many particles in a reactant vessel. So we can imagine if you have 1 or 2 particles, they have to colloid, right? If you have more and more, they're going to colloid more and more. So that's faster the reaction when the concentration goes up. Now the third one is actually catalysts. Catalyst I will discuss in detail later, but catalyst is something, some magic piece, you put it there to lower the energy level and things happens faster, right? Now the other one, surface area only for solids, right? And if you have a lump versus powder, powder will react faster, right? That's for the heterogeneous systems. Now the other one, it's really weird one, the nature of chemicals. That means water versus HCl. Of course, if you can drink water, you can't drink HCl, right? Or you can spill water, but you can't spill HCl. It'll burn the desk, right? Okay. Now this one. So this is, yeah, she got a nice picture here. PE diagrams. We're going to talk about reactant going to the product. So it's the potential energy diagrams, and I arbitrarily put 10 and some numbers here. So because y-axis is in joules, let's say 10, 30, 50 something, just roughly. And so what's happening here? How do we explain this? We can say the reactant to the product upward movement is called the enthalpy change, the delta H. That's actually product minus reactants. Products are at 30, reactants are 10, 30 minus 10 will give you plus 20. That is enter or endo, you including the heat. So that's endothermic, right? And from reactant to the hilltop, I call the hilltop, to the top of the bump, it's called the activation energy, or simply energy of activation. Right? Now let's look at the other type. The reactants are higher and the products are lower. So that means it travels downward. The delta H is 5 minus 25. That's a minus 20. It's a losing exothermic. That's exothermic. Right? Here the activation energy is less. That's why exothermic reactions are actually in one way easier to happen. Okay? And endothermics are harder because you have to give more energy for the activation, right? So makes sense? Now, so these 2 kinds we kind of want to know, and later I will put the catalyst into those graphs. Now, so I took another one. Look at the beaker of glass with some water. Some of the water molecules have a lot of energy, and some of the water molecules have less energy. This type of distribution is called the Boltzmann curve. It's something like people in your class. Some of them are very tall guys, some of them are shorter guys, and there is a whole bunch medium. This medium, the average temperature is, average kinetic energy is actually the temperature of that sample. Now, y-axis is number of particles. It's also called the population. Now, if 20-degree water sample, if I heat up to 30, what happens? They get more energy, kinetic energy. So the curve shifts to the right. As a result here, let's say I had X moles and this one also X moles. So that means you go from 30 to 20 to 30, your amount here is 2x in the Boltzmann curve. That's the whole point. That's what we are trying to look at. Now, if I go to 40 degrees, and even it will have even more, right? So that's the typical pattern when you, excuse me, when you heat a sample, the particles get more and more energy. So here is the activation energy. Why I'm putting that? Look at this one. In order to reach the hilltop, let's say it's a ball, you're pushing upward a mountain. So if you go to the hilltop, it's automatically fall down. So going on to the hilltop is actually similar to the activation energy. So let's say we have the activation energy here, 40 joules. Everything past that hilltop will go to the products. Everything before that will be reactants. So that's how we want to match this graph to the previous one. See this one, the hilltop is 40. Now if you have a catalyst, the magic, it will be the green line, which is, let's say, activation energy catalyzed. That would be, let's say, 35, right? So 35 would be somewhere here in the energy axis here. So that means whole lot of molecules are on the hilltop and they are becoming products. That's why we say every 10-degree increment will double the reaction rate. So it can be explained by Boltzmann. Okay. Now there's another thing, kinetic molecular theory, KMT. What's that? So all these particles are randomly moving with elastic collisions, right? And random energy, random moment. And then let's say this green and red dots are two reactants. They're moving around within this area, and then they colloid and make a reaction. Carbon plus oxygen makes CO2, let's say. Now, so there are a few things we need to see in order to have this reaction to happen. So oxygen and C should colloid this way to make CO2. If they colloid side by side, they may not make it. That's called the proper orientation. Now, if you have more and more particles, it's better for the reaction. If you have proper orientation, it's better for the reaction. And if you have more energy to reach the activation energy, that is better for the reaction. So actually it has to pass the activation energy, right? Remember, the hilltop is the activation energy. You need a little bit more to fall down, to go downhill, right? Okay, now, so that's pretty much the last part. So I'm going to talk about the rate is directly proportional to the number of particles or to the molarity of the reactants, right? And also I said there's energy role. So the energy is actually in this K, we call the rate constant. So the rate constant is giving you an idea about how much energy in it, and it's only for the rate that temperature. Now, so let's take three different reactions, right? R0 going to product, R1 going to a product, and R2 going to a product, like that. So I can write this rate law. Rate is K to the R0, R1, R2, right? We call these ones are zeroth order, first order, and second order. In case just nominally, if you have to know that, right? That means actually zeroth order has no effect for the rate, and first order has doubling the rate effect with the concentration, and second order has quadruples the rate. That's about it. Thank you.